Hi, Mike.
Hello.
Hello, Alexander.
Hello.
Hi, Julio.
Hi, Mike. Let's hope that our speaker will come up online. Hi, Christian, and welcome online.
If I unmute myself, it's easier to talk. Sorry.
Okay, no problem.
Hello.
Then. Hello.
Hello to all of you. I had just a quick question in advance. I do not remember anymore exactly what was the exact time I have for the presentation and then for the Q&A.
Well, totally we have 1 hour time slot here. I think that's something optimal would be 45 minutes presentation and 15 minutes for discussion, but it's not so strict.
That's perfect. I should be able to make it in time, so that should be good.
Okay, that's fine.
I hope you had a very good symposium so far.
Yes, we have, and this online technology and this platform seems to work very well. So that's surprisingly well. Everything is going or has been going. Yeah.
And it's also the more secure option. Just last week, 3 of my team members had been on a conference with in real life with real persons, I think now every single one had COVID. So
Oh, that's
So-
nice. So that the pandemic is not at all over yet.
now it's politically over and over in media, but not in reality.
Yeah.
So the virus is
Yeah.
not following political orders, unfortunately.
Yeah, exactly. All right, but it's time to start. Hello, everybody, and welcome to this plenary session. Today's plenary presentation deals with a very important topic in future energy systems, namely hydrogen and hydrogen-derived power-to-X products. Hydrogen and its derivatives are expected to be one of the main instruments in the decarbonization of the energy systems. Today's presentation is entitled Power to X Economy Will Be Built on Renewable Electricity and Green Hydrogen. And it will be given by Professor Christian Breyer from LUT University, Lappeenranta, Finland. Christopher Breyer is a professor for solar economy. His major expertise is the integrated research of technological and economic characteristics of renewable energy systems, specializing in energy systems modeling for 100% renewable energy on a local but also global scale. Energy system transition studies are carried out in full hourly and high geospatial resolution. Publications cover integrated sector analysis with power, heat, transport, desalination, industry, and negative CO2 emission options. Power to X investigations are a core research field for his team. He has published more than 300 scientific papers, thereof more than 130 in scientific journals. He worked previously for Rainer Lemoine Institute in Berlin, Germany, and QCells. He is a member of European Technology and Innovation Platform, Photovoltaic Power Systems Program of International Energy Association, a member of Scientific Committee of the European Photovoltaic Solar Energy Conference. He is also a member of National Finnish IPCC Group and a reviewer for the IPCC and a co-founder of the Disetec Foundation. His academic background is general business, physics, and energy systems engineering, and he is a PhD in electrical engineering. So please, Christian, the screen is yours.
Yeah, many thanks, Yuri, for the kind introduction. And now I'm not yet allowed to share the screen, so maybe I get that enabled.
Yeah, welcome now to share your screen, please.
Now it works. Thanks a lot. Okay, and now it should be possible that you can see the slides.
Yes, that's fine.
Perfectly. Okay, then let's get started. Yeah, so the question is what we can do with hydrogen, and should we call it, because this was also an idea, a hydrogen economy or power to X economy. And of course, for that, we better discuss a bit the features of the one or the other, or what type of energy system, at least from today's point of view, most likely will arise. And first of all, oops, maybe there is got something lost. No, on what resources we are talking, which we have available for our energy system. On the right-hand side, one can see the resources we used massively in the past, still today. So the fossil resources, whether it's gas or oil or coal and uranium. But they're first of all limited, and we have multiple issues and problems with all of them. In particular, climate change, but also air pollution, geopolitical issues. We can have nuclear accidents. We do not really know how to handle the waste and how to handle proliferation for nuclear weapons. So there are multiple issues related to those technologies, and in the end, they're not low cost. So the total cost, also societal cost, are rather high. And in particular, the inflation we have currently right now, the world is mainly driven by very high energy prices. On the other hand side, we have the option with renewables. They get a lot of attention and investments in recent years, but they still are on the minor share from the global energy supply. However, the potential is huge. As we can see on the right-hand side, there is this orange bubble representing the global energy demand, also with some growth until mid-century. The units are just to get the numerical value small, so terawatt years, otherwise it's not used much, this unit. But there we can see that already with solar energy we get directly from the sun, we get 1,000 times more the potential annually what we ever need as a society. Even if the energy demand would further grow, let's say by a factor of 2 until the end of the century, then the factor would be still a factor of 500. So we would not lack energy at all. But in addition, we have wind energy, we have bioenergy, we have ocean energy, we have hydropower, geothermal energy. So more comes on top. Even wind energy alone could fulfill the demand, but the others are more, how to say, supplement and complementary. Maybe what I should mention in addition, of course, it's not only the resources, it's in particular the enormous pressure we have with climate change. So we know we should limit the temperature increase to 1.5 degrees. Otherwise, major global tipping points are most likely to hit us severely. So meltdown of Greenland, destabilization of the Western Antarctic ice shield. In the very north, we experience the melting of permafrost. So in addition with emissions of methane, which is a very strong greenhouse gas, Amazon may be destabilized and to be converted into a savanna land, as we know it from savanna lands in Africa, with enormous emissions of CO2. Currently, we see the largest coral reef dying ever in human history. The Great Barrier Reef, the largest one in Australia, is just dying year by year more. So these are enormous disasters, not to talking on extreme weather conditions. Just think on the recent weeks with extreme early and high heat waves, in particular in India, also partly in Europe, extreme rainfalls. So all this should make us very worried whether emission of greenhouse gases is really a clever choice. Most likely not, so we have to fix the energy system anyway. Now is the question if we have better understood that, first of all, we have to fix the energy system, otherwise it will simply kill our civilization. We will not survive it. I think this is increasingly understood if we continue as in the past. The resources are available. Now is the question, what are the options? And maybe first of all, let's talk on electrification and what it means for efficiency. I think this is a home run now in our community here. But we have to be more aware how extremely inefficient the current energy system is. Let's start with electricity generation. If you have a thermal power plant, the global average of the thermal power plant fleet in the world is 35% efficiency. So that means 2/3 of the primary energy input is simply lost to warm up the water for fish, to produce artificial clouds, but it has nothing to do with efficiency. Most latest technology...
А ты думаешь, он собрался нефть покупать, что ли?
Okay, was not meant for me. So most efficient latest thermal power plants can be built up to 60% efficiency. We know that from gas turbines, combined cycle gas turbines under ideal conditions. So that will be, of course, much better. We could have combined heat and power, but still the global average is much lower. From a primary energy point of view, that's important to mention. With renewable electricity, we have a 100% or close to 100% efficiency. Why this is that high? The reason is the definition of primary energy. So primary energy is defined for the first time when man extracts something from nature. So that means digging out coal, extracting natural gas, having crude oil out of the soil, then it's primary energy when we extract it for the first time. Cutting a tree is the same. What does it mean for renewable electricity? And this definition was done decades ago with hydropower. So the flow of water in river streams is just a natural occurrence of something, a natural flow of something. However, when there's put a turbine, a hydropower turbine, then the first extraction of energy from nature in that regard is then already electricity. So due to that, electricity can be primary energy. And now imagine, of course, the principle is the same for wind turbine or for solar photovoltaic panels, because it's just radiation from the sun. We put a solar PV module there, then we have electricity. We have a wind flow. It's just something in nature. We put a wind turbine there, then we get electricity. So due to that, this direct electric extraction is much more efficient. When it comes to heat, the efficiencies of thermal processes, combustion processes in heat are much higher. So no doubt on that, it could be close or up to 100% if we have extreme efficient combustion processes for space heating, for instance. However, if we do the same with a heat pump, then the overall efficiency can be 300, 400, even 500%, depending on the overall conditions and types of heat pumps. So we get much more useful energy out from the electricity input we would use for the heat pump. So again, we would have maybe roughly a factor of 3 more efficient systems, in particular for space heating, compared to thermal processes if we link it to electricity. Transport sector, I think this is nowadays a no-brainer. If we have a car, to be honest, this is a combustion car, is a heating on wheels, because roughly 20% on average, annual average, from the fuel we put into a tank finally gets power on the wheels. And this is what we're interested in mainly. If we compare that to a battery electric vehicle, there we have a systemic efficiency of 70 to 80%. And nowadays, I think this year is the ultimate turning point globally to switch the global vehicle fleet to electric vehicles, because we have the first car manufacturers where a battery electric vehicle has the same cost when you buy it compared to a combustion car. However, it's more efficient and requires less repairs. So from that point of view, and in particular with the high fuel prices we see right now at the filling stations, battery electric vehicle may cost a fraction to get the same mileage done just from the energy throughput. So this for sure marks a turning point. To sum all this up, in the end, we have a very strong rationale for electrification, and this is efficiency. And I'm not yet talking on hydrogen. The point is, the message here is everything we can directly electrify makes a lot of sense from efficiency and finally also cost. And now a few diagrams why we will see a massive renewable electricity induced change in the overall energy system, and therefore the first time hydrogen appears. But let me start top left. And this is first of all photovoltaic systems. They're already low cost today. Since a few years, it's the least cost source of electricity we have in practically all countries in the world. Only in a few countries more, in particular in the far north, wind is still slightly lower in cost. But even in the Nordics nowadays, latest built systems, wind and PV, they're very close if it's utility scale. But the point is the learning rate, the learning curve is fully intact, so we can expect a further cost reduction in the decades to come. So minus 50% in cost should be no big deal in the next 20, 30 years. Similar, we see it for batteries. So it just follows the principle from solar PV. It's a modular technology with significant learning rates, cost come down. And this is the investment cost, what you see here from a utility scale battery system. They mushroom currently around the planet, practically all continents, to enable a longer lasting renewable, variable renewable electricity supply. So finally, it prolongs the service of wind turbines and photovoltaic systems in hours where we would have less wind or less solar energy. And this is currently growing very fast around the world. And of course, the even larger market for batteries is in electric vehicles, in cars, but this is here a cost function for utility scale battery plants. Top right, and now we come closer to the hydrogen. This is the expected cost digression, or a projection of cost digression from electrolyzers. So there is also the expectation that the costs drastically come down in the next few years and then decades. And historically, not yet that many electrolyzers had been built. So 20 or more, maybe a bit more than 20 gigawatts over the last roughly 100 years. And simply we did not need that much hydrogen. And in the last few decades, we did it with steam methane reforming from natural gas as a lower cost option, but this will change again. But in the early days, it was electricity-based hydrogen when it was introduced in Norway, for example, for fertilizer production many decades ago. However, what we see this year is a kind of an explosion in international demand on electrolyzer capacity. So the expectation for this year is that the annual production compared to last year will grow by a factor of 4. And these enormous growth rates strongly indicate that this is a very fastly growing industry, and due to economies of scale, cost will go down. This is also documented by the companies which enter this market, because several of the newly entering companies are known for high quality in huge volumes for fastly reducing cost. And some of them are from the PV industry, so they know how to run a paranoid business. And I'm rather sure we will see the same for electrolyzers, which will be most important for various parts of electrolyzers. And then, and of course, hydrogen demand. And bottom right, this is CO2 direct air capture. This seems to be a bit awkward technology since we have a CO2 emission issue, not a CO2 resource issue, but this may turn very fast because we have countries where practically all fossil emissions are on the list to be eradicated, and then there will be no CO2 emissions anymore at all. However, for hydrocarbons, whether it's fuels or chemicals, we still need CO2 as an input or carbon as an input to produce then a sustainable hydrocarbon molecule or product, fuel, chemical. And then is the question where to take the CO2. And of course, we can take it from atmosphere. This is surprisingly affordable. So the projections are for the next 10, 20, later 30 years that we get it on a cost level of 50 euros per ton CO2 just to produce it with extraction from air. Maybe a bit lower, a bit higher, depending where we get the heat from and where in the world such plants are operated. And this is only the first market. So this is direct carbon capture and utilization, DECU. And there will be a second huge market, CO2 direct carbon capture and storage, and DECs, because it's rather likely that we need massively negative emissions since we will overshoot the 1.5 degrees Celsius target. I think this is already carved in stone due to our failed international policies in the last 10 to 20 years. And to return to a more stable climate for our global civilization, we will have to go to negative emissions, and direct air capture might be a good opportunity. But the question is where then to put the CO2. So this is still requires a lot of discussion, but it's not the core topic for us today. So now let's already summarize the first few impressions. And now is the question, what's the role of electricity and hydrogen? Because we have to find good quantities in the end. And before I come to numbers and diagrams, maybe let's ask first a few questions. So the guiding questions might be, what types of energy service demands can be electrified at all? What types of energy services demands can be directly electrified? What types of these services demands cannot be electrified, but might be still, and not at all, so directly or even indirectly. Indirectly means we start with electricity and maybe convert electricity to hydrogen and then do something with the hydrogen. So that would be an indirect electrification. And for all types of energy service demands which cannot be directly electrified, what's then the role of hydrogen? So is hydrogen needed there at all, or what other options we have? And for what types of energy service demands hydrogen is needed directly? Of course, hydrogen might be important, but maybe not as a final energy carrier. And what energy sources are suitable for fulfilling the hydrogen demand. So if we know we need hydrogen, and I think it's without any doubt that we need hydrogen, the question is how much, but then it's still the question where the hydrogen comes from. So these are at least the core questions for the talk now. And I try to answer them either directly on this slide in the next block or then in the following slides. So first of all, some answers, and some of them will get more, how to say, food for thought on following slides, maybe not all. Technically, all energy services can be electrified, either directly or indirectly. But the question is, should we electrify all? But technically, this is now fully understood, can be done. And in the end, it's typically we need electricity, water, and air. Why water? There we get the hydrogen, and air, there we get either the nitrogen for ammonia, or we get carbon via CO2 for hydrocarbons. So this is due to that we call it that we need electricity, water, and air. And it seems, and for that I show then more results, that up to 90% can be electrified, direct or indirect. And this is also reasonable, so it makes sense. With the remaining 10% is then directly covered by bioenergy or geothermal energy or solar thermal heat. The problem with bioenergy is, so the more you go to the back, the more you find studies where the bioenergy share is very high. The only problem is sustainable bioenergy in the world is quite limited. Why is it quite limited? So first of all, we should use the arable land for food production, and we have a food crisis in this year. This highlights even more we should not misuse arable land for energy where we have better solutions for energy, but we should use it for food. And of course, biodiversity. So just cropping down rainforests in Malaysia, Indonesia, Brazil, for bioenergy production is, to be honest, a crime. That's not okay at all. We need these lungs for the planet, for a balanced biodiversity on the planet. So all this limits bioenergy, and then in the end we talk on wastes and residues, and this is rather limited. So this may limit bioenergy to maybe a 5, 6, 7% contribution of primary energy demand. Geothermal is a bit unclear how low cost, how much we may get, and solar thermal is always in competition with solar electricity, but there might be also sweet spots. From a final energy demand perspective, there might be only 50–60% directly electrified. And the reason is not everything can be really electrified. I will come to that in more detail, but just think on international transportation, marine transportation, international flights with thousands of kilometers that will be not done electricity based, at least for many decades. So currently we do not know a technology which could enable that. And due to that, we need dense energy carriers. However, the same is true for chemical industry. We simply need the hydrocarbons for plastics and for other chemical products. And this is also true for the one or the other segment in the energy system. Heat for space heating, that might be mainly supplied with electric heat pumps and maybe other heat sources. I mentioned geothermal, so deep geothermal, solar thermal. It could be bioenergy where it's sustainably available. That's all fine. But these heat pumps finally deliver heat as a final energy, but the main source will be electricity. But of course, we could also have recovered heat from conversion processes. So, but all in all, there might be a lot of electricity in the heat system. And we know that from Nordic countries that there is a high share of heat pumps nowadays installed on individual buildings, but also on district heating level. So that's now a well-established technology. Marine and aviation fuels are already mentioned. Due to the long distance transport, chemically dense energy carriers are required. The question, of course, will be, is this hydrogen or something else? This is not yet clear, but it has to be chemically dense energy carrier. Industry, energy carriers are required, as mentioned just briefly before, with chemicals, but also steel making and also other products. I think on glass making. So for float glass production, currently a very clean methane input is used for these high temperature processes. This might be very well substituted with hydrogen. Whether this is could be all electric. I'm not yet sure. Maybe hydrogen could be a good option there. However, and this is very important, hydrogen is the smallest molecule in the universe. This has consequences, and already a consequence is the extremely low liquefaction temperature. So with minus 253 degrees Celsius. So this is close to the minus 273 degrees Celsius we have, or 0 Kelvin we have in the atmosphere, in outer space. So that makes it very tricky from a technical point of view. Technically it can be done, but if it's tricky, it means it's expensive. And when something is expensive, it's not helpful for energy systems. Okay, now I will show some results, and the results had been created with an energy system model. Due to that, I just wanted to briefly mention the model with what we have done it. So this may help to get a bit more credibility on the following results. It's the so-called LUT energy system transition model. It is a bottom-up energy system transition or energy system model with all main features you need for any energy system, whether it's fossil or nuclear or renewable based, it doesn't matter, all those components are there. However, this energy system is optimized that power-to-X processes can be described as, how to say, realistic or as meaningful as possible. And it can be used for up to 100% renewable energy system solutions, really to test the limits. So all the renewables are there, different storage options, flexibility options, and interaction of all these energy systems and sectors. So it can be also used for sector coupling studies due to that. And the key feature is, of course, the hourly resolution, because if an energy system is mainly based on solar energy and wind energy, which is not available in every single hour when we really would need the energy, due to that, we have to better understand how to link our inelastic demands. We want to have now this conference online. We need the electricity now. So there is no compromise, full inelastic demand. However, this has to be somehow decoupled from the variable input from the renewables. And this we do on an hourly resolution, and we use as much real historic data as possible, meteorological data, but also demand data. And it covers on bottom right, you can see industry. So it's even more, it's an energy industry system as we operate it now. And just to give an overview on the model, this is this top right box. This is from a reference published 2 years ago. We have been not involved there, so that's even more important. We have been compared to other energy system models on the longer term and, how to say, rated in technical features as resolution, whether resolution in time, in space, in techno-economic detail, sector coupling is good enough. Is it transparent? Does someone understand what we're doing there with or what is done in these models? And all in all, the ranking is rather high from our model, so that's rather good. So it's one of the international leading models when it comes to such features. And just a recent publication, this is the table bottom at the bottom. This is now from a publication from my team, where we have compared on a basis of more than 500 scientific articles, most of the last decade, what models had been used to describe really highly renewable energy systems. So it's written there 100% renewables, but at least 95% renewables was the threshold to be considered here. And then we are one of the 2 leading models which are used for these analyses, and several of the other models you may have heard before. So TIMES is a very much used model, but not so much yet for highly renewable systems. But this just as an overview. So then now to the results. This is a global transition study where the target or the scenario had been to go from the present energy system. You see here the breakdown of the energy used in 2015. So a lot of coal, oil and gas, and then the rest. But to go to a zero emission, but 100% renewable energy system in 2050, and with this machinery. So full hourly resolution. And you see here the high geospatial detail. So there we have the world in 145 regions. And large countries have then multiple regions. So Russia would have 7, India has 10, but large Australia, not that many people, but just from the geospatial dimensioning large than two regions. The US has 14 regions, Brazil has 5, and so on. But several countries are then a single region. Just take France or Egypt or others. And the color code indicates when a single source would have more than 50% supply of the overall energy for the system in 2050, and yellow indicates a solar system. This bright blue indicates a wind-based system. Dark blue would be hydropower that we only find in Iceland, and green would be a mix of different options. Another single source would have more than 50% share. And then you can see that's maybe not that surprising that across the Sunbelt in the world, solar is the dominating source. And this has a consequence, is in particular based on the low cost. And the question is this a tree hugging scenario? So could we not afford it at all due to high, maybe perceived cost of renewables? But that we could really show it's not the case. The levelized cost of energy, so that means all annualized system costs to run such a system, even in the transition, with the legacy cost of maybe today, it might be still a bit higher in cost than in 15 years in investment. So all this legacy is included still. Divided by the total final energy demand. So this is how we have defined here levelized cost of energy. And there you can see it's a practically cost-neutral transition, which is quite attractive. So we get a system without CO2 emissions, without air pollution, with much less geopolitical stress, but for the same cost. Should be attractive. And now coming to primary versus final energy. And there you can see from a primary energy point of view, we would end up in 90% electricity. And this is then renewable electricity. This was the 90% I mentioned before. So step by step by step, fossil fuels are phased out. We still have some direct heat, and then of course some bioenergy, and the rest is electricity. When it comes to the share of the final energy, by the way, here you can see only 45% of electricity. However, a major share of the heat is finally from heat pumps. So maybe it's fair to have this share of electricity used for heat pumps allocated to electricity, and then it will be more than 50% or around 50%. But still, and this is important, maybe all in all, 50% of the final energy demand is electricity and not more. So first of all, this already tells us right from the beginning that a lot of the electricity from the primary side is finally converted to something else on the final energy side. So this has already this power to X feature, and this is one of the bullets I had added here. So this power to X, what is the X? It could be heat. I mentioned heat pumps. It could be fuel, so we convert electricity to hydrogen, but it can be jet fuel, it can be ammonia, it can be methanol, it can be methane. So all what we know as a major fuel from today, we can convert it to that. It can be directly mobility. So of course it's still electricity, but when we have an electric car, finally we talk also on mobility. It can be clean water, so seawater desalination. We can have refined materials, so we can convert it finally to steel. It can be aluminium, that we do already today. Finally the bauxite we refine to aluminium, mainly using then also electricity, at least in the final step, or chemicals. So it will be more complicated in the future to talk on electricity from this perspective. Now let's go a bit more in the inner core of this power to X and hydrogen. So first of all, if we start with electricity, it does not to be necessarily renewable. It could be also other electricity, but renewable electricity is most attractive since it's so low cost. And then with electrolysis, we have hydrogen. And now is the question what we do with this hydrogen. First of all, we can use it directly. And if we would have a huge share with this direct hydrogen demand, and this across all energy sectors, then I would say it would be justified that we would call such an energy system hydrogen economy, if that would be the most integral linking element of the rising energy system. But I will show on following slide that's not. Then, of course, it can be converted to hydrogen with CO2 in methanation, and maybe then in liquefaction. Then we would have LNG. We could use this in a gaseous form. Then we have methane. We could go for a Fischer-Tropsch process. Then we have diesel, gasoline, jet fuel, naphtha as a byproduct, quite nice, can be used then as a chemical feedstock. Or we can go to methanol synthesis, then we have methanol as a feedstock. By the way, methanol can be also with another process converted again to diesel or gasoline or jet fuel. So we have two technological routes available. And if we have nitrogen extracted from the air, then in an ammonia synthesis, we can go to ammonia, which is then the most relevant feedstock for fertilizer production. But by the way, methanol and ammonia, of course, is currently strongly discussed to be a major fuel for the marine industry. Currently, both are in parallel. Ships are ordered with methane propulsion and with methanol propulsion and ammonia propulsion. Whether it will be more the one or the other, we do not yet know. So, but now let's come to the energy system, where we come from. So this is a description of this 2015, what I started a few slides before, energy system. And now from an energy flow perspective, on the left-hand side, you see the sources, all primary energy sources. On the right-hand side for what we needed. So we need it for power, electricity, for heat, for transportation, and there are losses. And where it comes from, it's mainly fossil oil, it's fossil gas, it's fossil coal, and that we use across all these energy systems, but or energy sectors. But the sectors itself or among each other, they're not really coupled. So all these fossil fuels are used in all these sectors, but otherwise these sectors are more or less separated. And now this is the energy flow of what I showed before for 2050, and there it looks different. First of all, the fossil stuff disappeared because we cannot afford it anymore if we want to survive as a civilization. And I do not go into details of fossil carbon capture and storage. Maybe in a discussion round we could go deeper there, but in the end it's super expensive and air pollution remains still. So an electricity-based energy system, a lot of the electricity is used directly. Other parts of the electricity we would use for the heat pumps, so that the heat supply can be organized. Other part of the electricity is then used directly for the transport sector, in particular for battery electric vehicles. But of course, the railway system is strongly electrified. We have electric ferries. This is now the default ferry technology in the Nordics, for instance. And the first electric flights are expected in the next few years. Already Norway has a target that in 2040, all flights 500 kilometers around Oslo have to be electric. Whether it's achievable with then ready technology, we will see, but there is a lot ongoing right now. So, and now we see this major stream in the mean here, the blue one, and this is hydrogen. So a lot of the electricity is converted to hydrogen. And this hydrogen, and this is then important, is further converted to either methane or Fischer-Tropsch. But a part of the hydrogen is also used directly. So hydrogen plays a role, but within an energy system which is built on the idea we have electricity and convert the electricity to finally fulfill our final energy demand. Now let's go a bit more detail. What's the role of hydrogen for such a system? So first of all, we have a power to hydrogen and then to X. So this emerges as a main feature for the arising energy system. And this X can be then hydrogen used for aviation directly as hydrogen, or in the form of jet fuel, as a marine fuel directly again as hydrogen, or as liquid, so ammonia or methanol. By the way, diesel from Fischer-Tropsch plant would be also thinkable, but it might be too expensive. And then on the road, maybe some hydrogen fuel cell electric vehicles. However, it seems to be that they're only built if there are subsidies. So the major car, bus, and truck manufacturers in the world, they're all bet on battery electric solutions, simply due to much higher efficiency and lower cost. So the systemic efficiency of a battery electric vehicle compared to a hydrogen fuel cell electric vehicle is a factor of 2 better. And of course, this has a strong impact on overall cost. Yeah, and we may need some hydrogen for high temperature industrial processes. Hydrogen is for sure, and that one can be seen if one would go in more detail to the streams, but you can check it in the provided reference. So in the supplementary, the diagram is there, and then you can deep in more detail. So hydrogen is not used for space heating and only very limited for seasonal power balancing. So the reason is it's simply too costly. We have better options for that. However, this study, at least to the knowledge of the authors, has the highest hydrogen demand ever published, more than 40,000 terawatt hours of hydrogen. So this number here. And electrolyzer demand, which is more than 10 terawatts of electrolyzer capacity, which is by orders more than we have today. So let's see whether in 2050 we have done such an energy system. Now let me talk a bit more on the e-fuels and chemicals, because this was also part of the introduction of myself, that we do not only talk on hydrogen, but of course also what we can do with the hydrogen. And this is more visualized on this slide. So first of all, we're talking on hydrogen directly, and this can be produced mainly with two main pathways. So we have water, we have electricity, we have an electrolyzer, and then we produce hydrogen and can use the hydrogen. Today, we do it with methane and steam methane reforming, so that we get hydrogen from there. The present issue is that it's much too expensive, the methane, what we can get in the markets. So it's not affordable and may even bring companies into bankruptcy due to this extremely high cost. And of course, we have CO2 emissions, which is of no help at all. So in a sustainable energy system, the CO2 emissions have to be eradicated anyway. But this is hydrogen. Then we have ammonia. Ammonia means we need the hydrogen, and then we need from the air the nitrogen, and this air separation unit again can be run with electricity. Then we have the nitrogen and the hydrogen and get ammonia in the Haber-Bosch process, 100 years old, so state-of-the-art technology since decades. This is not really new. Methanol might be then the future dominating platform chemical for chemical industry. Again, there what we need is CO2. What we need hydrogen, and there is the CO2 we could take from air with direct air capture units. They exist also since decades. They have been developed in the 1960s for nuclear submarines and for space stations. So, but this technology is now further, expanded and applied for new purposes. And the major input of the energy is heat. So whenever we have very low cost heat, it's super attractive, but heat has to be only 100 degrees Celsius, which enables also heat recovery, which is of course also attractive. Then methane, similar to methanol. So we need a CO2 source, we need hydrogen, and in a methanation process, we get the methane. And Fischer-Tropsch, there we would have a reverse water gas shift process to have syngas. Then we would have the Fischer-Tropsch reaction. Then we need a so-called hydrocracker, and then we get different fractions of the liquid. So it's gasoline, diesel, jet fuel, naphtha, others. And we could still have such fuels on the biomass route. So this is what is all available. And unfortunately, I cannot go into much details of all what this means for the cost and where in the world we can do that best. On top, you see ammonia, then you see hydrogen, then methanol, and bottom, it's Fischer-Tropsch liquids. So we have invested much time and resources to get it on this level. So all has been calculated here in 50-kilometer resolutions, full hourly optimization with such processes, but in more detail. So there's more technological detail to get these cost numbers derived, and we have it typically for 2030, 40, 50. Not all of that is fully published. So the hydrogen is fully published and the ammonia is fully published, and the rest is in earlier forms available, but not that in this latest insights. But in principle, all this is doable and it's affordable. So that's the key point. By the way, green ammonia is today, so electricity-based ammonia is the least cost form of producing ammonia for international markets as of now, as we speak now. Let me just give a brief shot on solar hydrogen. So even that is now possible with very low cost, that directly solar electricity on a large utility scale scaling is used with electrolyzers, and this would enable very, very low hydrogen cost, lower than all other options we have right now. So whether we do steam methane reforming with CCS, so carbon capture and storage, or without. So green hydrogen is rather clear will dominate the hydrogen supply. So this is based only with solar, but solar and wind hybrids maybe then the more suitable option. But I personally would be not surprised if we would see explosion of such projects announced in the weeks, months, quarters to come, because it's simply low cost. Now I come step to step more to the end of the presentation, but I would like to show you a latest insight with a more diversified view with latest model updates, which is not yet published, but hopefully in a few weeks or even a few days, we may have a report on that. Otherwise, in autumn, it depends on our client, but this is a very ambitious energy transition study for Europe, where the idea is in 2040, it should be zero emissions, but this is how the system looks like in 2050, but the target is in less than 20 years from now, it should be zero emissions. And here you see there will be some imports. So this is added. There's still some sustainable bioenergy. A lot of energy is taken from ambient heat for heat pumps and then electricity based. You see a lot goes directly to electricity. Then industry is in higher level of detail there with cement, steel, chemicals, aluminum, pulp and paper. And there we see that in particular, this electricity to hydrogen to methanol, ammonia, and green steel is really a main demand for hydrogen, but those industries do not really need the hydrogen. They want to have methanol and ammonia, but hydrogen is the most important energy carrier before. Then we have the heat segment or heat sector with space heating, domestic hot water. There it's mainly electrified with heat pumps. And then we have the transport sector where we have a lot of direct electrification for electric cars or vehicles, also buses, trucks. We need kerosene jet fuel for the aviation industry, maybe some direct hydrogen. This is not yet so clear. So Airbus is developing such airplane. And for the marine sector, it's mainly methanol and ammonia. Of course, this is currently discussed as the main marine fuel in future, but still we see a lot of electrolysis and hydrogen, but it's dominated by electricity. So this is very similar as the energy flow diagram I showed before, but we have more details here and more model features. The question you may have in mind is, but if we have this variable solar and wind, is it really a stable system? And this is from a report published 2 years ago, a diagram for the best week in Europe in a 100% renewable system. This is top, and the worst, which is bottom. First of all, we see it's always stable for every single hour of a year. So this is shown on that case. However, there's a strong difference, and this is so important when we talk on hydrogen and power to X. This is this gray part here. This is very, very strong if we have a lot of solar and wind electricity in the system. And as you can see here, this is called power to fuels. So this means the electrolyzers run when there is solar and wind available and then convert the electricity to hydrogen. This is put in a hydrogen buffer storage, can be underground, rock cavern, salt cavern, even steel tanks. It would not disrupt the business case. And then this can be further converted in a synthesis to what we need, Fischer-Tropsch fuels, ammonia, methanol, what else. And if we have then really a lack of those resources, so winter week, this is typically November in Europe, where we have a lot of fog, not good sun, not much wind in a foggy week, then this gray part would be practically zero. So then this will be not produced, but we have hydrogen in the buffer storage so that it can be discharged from there. But this hydrogen typically never comes back to the power system because we have enough electricity capacities directly usable. So let's compare now a power to X economy and a hydrogen economy. What speaks for the one, what speaks for the other? Let's start for power to X. So 90% of all energy industry demand will be finally based on electricity as the dominating source of energy. So this is a strong, how to say, argument to power to focus on the power part. Electricity can be converted in all forms of energy. That makes it universally usable. Electricity as a final energy carrier is most attractive due to high efficiency. The power to X conversion can be found in all energy sectors in various forms. So this is a strong argument to call it like that. For hydrogen, hydrogen is a very important element of the rising energy system, no doubt on that. Hydrogen, however, is typically not attractive as a final energy carrier due to all the limitations, and hydrogen serves mainly as an intermediate energy carrier to produce something which has more value for us for the final use. So sources other than renewable electricity seem to be not much relevant, which is also important not to call it hydrogen economy. And this is due to cost, emissions, and limits. So other sources would be fossil fuels, but then we would call it blue hydrogen with carbon capture and storage, but this is expensive. expensive. We could do it based on coal, but then we still have the emissions. It's also expensive. We could do it based on nuclear, but again, it's expensive. We could do it based on bioenergy, but this is limited. So due to that, there seem to be not many other credible rules. And now to do a synthesis of that, so power to X economy versus hydrogen economy. So the rising energy system represents substantially more features of an electricity or power to X based economy than of hydrogen related features. And due to that, power to X economy is the most inclusive and comprehensive description of the rising energy system. And now let's summarize and conclude my talk. The energy transition reaching, so we have energy transition reaching zero CO2 emissions by mid-century, and this is feasible technically and economically. The direct electrification use or electricity use is most efficient and least cost. However, not everything can be directly electrified. Therefore, indirect electrification is still very important, but it's scalable, affordable, and leads to a sustainable energy industry system. And power to X economy is the more comprehensive description. Then many thanks for your attention, and in particular to the team. As you can see here, a latest picture from all team members, because without the great work of all my team members, these kind of results would have been never created. And then I'm very happy to take all your questions.
Thank you, Christian, very much of this. Your very informative and interesting presentation. And now we have 10 minutes time left for questions from public. So please, if you had anything in your minds.
Yes, I wrote some questions in the chat, but I could repeat it if possible.
Yes, please.
So first of all, thank you very much for interesting presentation. So now I have just a couple of comments about the elements of the batteries. So the batteries require not very rare elements, but let's say lithium and cobalt, and only a small portion of lithium we have in Europe, that's in Portugal. So other suppliers are outside of Europe, namely in South America. About cobalt, so the largest supplier is Democratic Republic of Congo. And in Congo, about 15% of the kids in the age between 5 to 17 are engaged in child labor. So I think that this component should be, this human rights component should be taken into account. This is my opinion.
Yeah, let me, oops, there is some echoing. Let me briefly comment on that. First of all, we did deeper investigations on the limits of different materials, and due to that also, of course, of batteries and lithium. And it seems to be, even with a very ambitious energy transition, we may have enough lithium to get all this done from mines and salt lakes as we use it today. So there should be slightly more. We have not really detected in all different scenarios. We did until the end of the century, not only 2050, and we did not find a physical shortage, but it is close. So due to that, this we have to consider. But we had been more conservative on the energy density. So with more breakthroughs in battery technology, the energy density, so that means electricity stored per used lithium, the specific lithium demand, then this would be improved the situation. And we have not considered any kind of breakthrough, but this is currently intensively investigated to extract lithium from the oceans, because we have a practically unlimited lithium deposit in the oceans, but it's very diluted. And the question is, do we find energy efficient enough processes to get it extracted? We have an accepted paper, which should be every single day online, how to extract lithium from desalination brines. So when we do seawater desalination, because there the salt concentration from the brine is a factor of 2 higher than in the oceans. So it's more attractive to extract it from there. And even if at least the projected desalination demand until 2050 would be done with seawater desalination and lithium extracted from those brines, then up to a quarter roughly of the global lithium demand could be covered by that. Still, any other technology than lithium in cars, mainly, or stationary battery would be helpful. And currently, natrium-based, natrium-ion batteries or sodium-ion batteries are currently on the rise. So they seem to be very close to be used by car makers. And when it comes to cobalt, I'm not worried at all. And the reason is we can fully get rid of cobalt in lithium-ion batteries. I think in the first quarter of this year, a substantial fraction, at least a quarter, maybe more, of the batteries used in Tesla cars had not any more cobalt included. So, and the largest battery manufacturer in the world, which is CATL from China, produces cobalt-free batteries for their customers now. So I think cobalt we get rid of the table. That's good. Otherwise, we should be very concerned. I would fully agree with you, but we get rid of that. And lithium is at the edge, I agree, but we may get different additional sources, and we have not bad chances to get at least a second major chemical or chemistry next to lithium available, maybe at least for stationary batteries. So should be doable. I will be not too much worried on that side.
Thank you very much.
Thank you. Then Francesco Casella has raised hand, please.
Yeah, thank you for the very interesting presentation. I really loved it. I had one question that you partially answered already with reference to northern Italy, which is where I live. Basically, there is very little sun and very little wind from November and January. So my question was, what do we use for electrical power and space heating? Apparently, what you are proposing is that we have so much excess, so to speak, PV installed that we simply switch off the electrolyzers and there is enough. If I understand it correctly, then basically what we should do now is to install PV like crazy. Is that what you would recommend?
Yes, but not only. So first of all, when you go for really ambitious energy transition studies for Europe, then depending on the level of ambition, at least 2,000 gigawatts of PV are needed in Europe, maybe up to 6,000. So the range is still high. There is still a lot of discussion. It's also the question on the relative competitiveness of solar to wind, in particular wind offshore, but also the question, do we have enough area for all the solar? So due to that, we need highest efficient photovoltaic modules so that the area demand can be limited. But to be honest, the zero impact areas, we all know our roofs of the buildings, so they need to be covered for sure. Also the facades, because PV is now so low cost that if you just put PV on the facade of the building, the yield there is not that much lower if there is not a huge shadowing issue. So that electricity from the grid would cost much more, and for sure also in Italy. So that would be highly attractive. But of course, it's not only solar. You mentioned northern Italy, so this is I would say, the bright side of life. So there is excellent hydropower potential from the Alpine region, whether it's then partly in Italy, most in Switzerland and in Austria, with hydro reservoirs where it can be used in particular a lot in the winter half year. And then, of course, we need to have in mind we need large European interconnected power grids, more than we have today. But Italy has not a bad grid infrastructure due to that, because a lot of electricity is still indirectly imported from France. Currently, I guess, rather expensive since the French nuclear reactors are by 50%.
We're not doing that right now, I guess.
Shut down. No. Yeah, exactly. But this very strong power infrastructure is very important in future. Then to distribute the wind capacities across Europe, because we will have of course along the coastlines most of the wind capacities, and more than in those regions is directly needed. And with a strong power grid, this can be then distributed across Europe. And I'm very sure in the winter half year we should use a lot of wind electricity and heat pumps, because solar is simply a bit lower. However, for the case of Italy, maybe it can be then sent from the southern parts of Italy via the grid to the northern part. In the southern part, maybe heating might be even not needed, but maybe in South Tyrol or in other northern Italian parts might be needed. But then it could be maybe still in the same country imported from the south. In the end, a strong electricity grid infrastructure is most important. Also, no doubt on that. But maybe most likely not with seasonal storage, because this will be a rather high cost option. And I think our other complementarity and flexibility options are lower in cost.
Yeah, exactly, because I mean, there's been lots of talk about using hydrogen as a storage medium, but the efficiency is so dismal that it doesn't really make any sense.
To be honest, the more you have a really strongly built sector coupling comprehensive energy system model, you do not find hydrogen as a heating source. It's simply too expensive, and we have other options. So the more one narrows down the perspective on the energy system of only a few single components, of course, the more the high cost backup solutions or backstop solutions come on the surface. But the more detailed the energy system is regarded, the more we find the lower cost options. And in particular, in northern Italy, I'm very sure there is also waste and residues from biomass, from forest industry, for example, or from other agricultural activities, which can be used also in the winter half year, in particular for bioenergy, combined heat and power plants, partly in district heating, or we know these wood chips, which can be partly used. So there's then a variety of options, and regionally, maybe the one option is more attractive than in other regions. But if there is bioenergy available due to larger forest regions as a byproduct, then it's a good solution.
Thank you.
Okay, thank you. We start to be near to use all of our time, but I have one very short question. It's about this. You mentioned that you use this LUT model tool. Is it open source tool, freely available, or licensing, or is there other researchers, other groups, any possibility to use that tool?
Not yet. So it's the plan to have it as a open source tool available. So we prepare for that, but we want to do it really nicely. It would be easy for us to have it as open source. We would just have to upload the source code somewhere. I have a nice paper on that, and that's it. But it would be not helpful because this is so complicated. You need, first of all, the data environment to really make it useful as such a complex model. And it has to be explained better than we do it in the supplementary of papers. So with a documentation, and then there should be tutorials just to get it easier started and run. That requires some time. So due to that, it's under planning, but it may still take the one or the other quarter to be available. But we have increasingly noticed the value add is really to share it and to have it available for the community. Yeah.
Okay, thank you very much, Christian, with this very interesting and nice presentation. So thank you very, very much.
Many thanks. Have been a pleasure.
Okay, and then I think that it's time to proceed in our symposium program, and then it's time to say goodbye. So it's the time for the closing ceremony for this 11th symposium on control of power and energy systems. We have had 3 days full of excellent presentations about power and energy systems related topics dealing with control, modeling, optimization issues. And now it's time to wrap up this our symposium. Sorry, now I am doing something wrong. Yeah. So my can you let me have the screen?
Yes, you're free to share your screen now.
Yes, thanks. Oh, sorry. A little hassling. Okay. Okay, now you should see my screen. So, as I mentioned, it's time to wrap up this our symposium. It's time for closing ceremony. And first, I would like to show some statistics, what we have had so far. And this our symposium, we had totally 148 submissions submitted to our symposium. And after the review process, we have 95 accepted papers and 40 papers were rejected. And then we have quite many withdrawn papers, 40. And that big number is because we have this 1 year postponing of this our symposium. The symposium should have been organized already 1 year ago, and we have over 60 papers submitted with that original date, but then quite many of them were withdrawn and perhaps presented in some other venues. So that's why the number of those withdrawn papers is so high. And we have 5 excellent plenary papers included in our program, so that totally we have exactly 100 presentation, regular sessions, invited sessions, and plenary sessions. So quite good solution. We have had 116 registered participants in this conference platform, so quite good number of participants in our systems. We have papers from totally 21 nationalities, because originally the symposium was supposed to be organized in Russia, and this can be seen also in this number of papers from different countries. Most of them have come from Russia, 40, and from China, 10, Germany, 6, Japan, 6, Portugal, 5, then France, Mexico, South Korea, 4, Finland, United States, 3, Cuba, Hungary, India, Ireland, 2, and then from Italy, Colombia, Denmark, Nepal, Romania, Spain, and Sweden, we had 1 presentation. So we have quite international content in our program, and I'm very happy of that. And also very good number of registered participants, so it's very good. Our program, those presentations, they were built in 16 sessions in 3 parallel tracks. We have 1 track, so-called cyber track, which includes, let's say, the computer-based systems and this kind of things related with computer technology. And then optimization track, where we collected the papers related with system optimization, system planning, and this kind of things. And then this technology track, where we have then the different kind of generation technologies, transmission technologies, and different things related with this kind of things. As you have already noticed, all our regular and invited sessions were pre-recorded video sessions, which can be accessed at any time via Conference Compass platform. the plenary sessions were live sessions, real-time sessions, and in every session we have from 30 to 40 participants in each session, which is also a quite good number for the participation. Then we have evaluated all the papers submitted and presented in this conference, and with the session chairs together, we have ranked the papers, and the best paper award in this symposium, it will be given to the paper titled "Using a Computer Simulator to Create a Digital Model of a Combined Cycle Gas Turbine Power Unit." And it's presented by Edik Arakelian, or written by Edik Arakelian, Sergei Mesin, Fyodor Pasachenko, and Anatoly Kosoy. I wonder if there is any of the authors available online now. No. Okay, but congratulations to them. So, and this this diploma will be sent to them via email. And next, we will have some closing words by IFAC Secretariat. Dr. Dimitri Poshel, are you available and online to say something?
Here.
Okay.
Hi, Irjo. Thank you for the invitation. Sorry that I couldn't make it to attend all the sessions, but I'm happy to be here and see that the symposium went very well. So, dear participants, dear program committee members, and dear organizers of this 11th IFAC Symposium on Control of Power and Energy Systems, I take advantage of this closing ceremony to remind that IFAC is a multinational federation of national member organizations, each one representing the engineering and scientific societies concerned with automatic control in its own country. The purpose of the federation is to promote the science and technology of control in the broadest sense in all systems, whether, for example, engineering, physical, biological, social, or economic, in both theory and applications. IFAC is also concerned with the impact of control technology on society. So on behalf of IFAC, let me congratulate you today for the fruitful scientific exchanges to which you participated actively during these 3 days. They perfectly align with IFAC objectives, combining theory and application in the field of power and energy systems that have a key impact on society, considering the global environmental changes. The vision for IFAC is to be the worldwide federation for promoting automatic control for the benefit of humankind. And its mission is to promote the science and technology of automatic control through technical meetings, as today, publications, those papers that will be in papers online, and other means consistent with the goals and values of IFAC. So congratulations to the program committee and to the organizers for making possible the symposium. As IFAC Vice President for Operations and Secretary, I am well aware of the many issues you had to face, and I welcome the adaptations that enabled the scientific event to take place, at least in virtual format, even though we would all have preferred it to be in presence as initially planned. As our president, Hajime Azama, likes to say, solidarity and cooperation are important and essential to tackle scientific and societal issues. Let me wish that IFAC will continue as it was for the past 64 years of its existence, a place where this cooperation is inclusive in the diversity. Everyone being active in the field, in the automatic control field, is warmly invited to register as IFAC affiliate. Registration as IFAC affiliate is free, and it gives access to several services, such as, for first one, receiving the IFAC newsletter, and note that the latest format includes a control-oriented cartoon, which is a novelty since several months. Another service is receiving alerts about the IFAC conferences in your specific fields of interests. And soon we're updating some computer platform. Soon you will be able to update and adjust your own fields of interests directly in the platform in order to follow what are your fields of interest. Third thing, being an IFAC affiliate gives you the benefit for reduced registration fees at IFAC conferences. This is a new feature that is starting currently. Typically, it will be €10 less expensive for IFAC affiliates than for non-affiliates. Fourth thing, being an affiliate allows you to participate in technical activities and thus helping the community, for example, as IPC members. Fifth thing, organizing IFAC conferences. As you did today, congratulations for the organization. And IFAC is building new services to make this organization cheaper and easier. And one example is the IFAC conference app that you are currently using for your conference, which is great. Being an IFAC affiliate allows you to participate in IFAC journals. It also allows you to apply and obtain IFAC awards. And you can also apply to IFAC, the IFAC Activity Fund, which enables new initiatives such as a new In Control podcast, for which we will be advertising soon in the newsletter. And there are more services to come in the future. So I encourage you, if you are not already an IFAC affiliate, everybody here to become an IFAC affiliate and to discover all these features. And I will be very happy to hear any positive or negative feedback about these services, and we'll try to improve all the time. So once again, congratulations for this 11th CPES. Thank you.
Thank you, Dimitri, very much for your kind and wise words. Now I think I have not warned Mike, but I think that you have had a very special role in organizing this meeting. And would you like to say something about this process? And what do you think, how we succeeded?
Thank you very much for giving opportunity to express my feelings now. I'm happy that the conference, after all difficulties we had, that it is coming smoothly. And I can say that although they're having the closing ceremony now, our program is not finished for today, because we also have regular and invited sessions in an hour, and I invite everybody to participate. Our live sessions play a special role in our conference. They are not to make presentations, but for communication, for discussion. I think that communication and discussion are the main assets of any scientific event, and we should take opportunity to ask a question, to see our colleagues after these 2 COVID years. I saw many of them during the recent 2 days, and I believe to see you all on our invited and plenary sessions today. Thank you very much. I would like to thank also IFAC for providing us the virtual conference platform. I think that the Conference Compass is one of the best virtual platforms on the market, and it's really useful. I can say it as a user, and I believe that IFAC will continue collaboration with this company, and we'll see many virtual conferences and many offline conferences supported by these wonderful capabilities. interactivity and sharing full papers and pre-recorded sessions and so on. Once again, I'm happy to see you all after the long preparation, and I wish you to enjoy the event. Thank you very much.
Thank you very much, Mike. Okay, and in addition with Mike, about those special thanks, because he has been the main person to build this event, the program, the running all the systems and so on. So once again, very great thanks to you. And also I'd like to thank IFAC Secretariat, Katarina Willigshofer and Dimitri Poschel, giving the new home for the organization to our symposium, because we have those problems, and in the beginning of this year in February it looks quite difficult how we will be able to organize the system, but with the kind help of IFAC Secretariat we managed to do that, and now we had these excellent results. So once again, great thanks to IFAC Secretariat helping us in this thing. And then also, I'd like to thank very much all the associate editors and reviewers who take care of the review process. As I mentioned already, we have almost 150 papers evaluated originally in this system. It's a very big job, and all the editors and reviewers, they have made a wonderful and great job to make this possible. And last but not least in that way, all the contributors who have made this event by preparing a presentation to this venue. So we also like to thank you, because you are the one who made this event, and without you there would be no symposiums, this symposium or next symposiums. So that please be active to write papers and so on, so that we can continue with those different events. And finally, I have nothing else to say that have a nice summer, and let's meet next time. In next summer, there is IFAC World Congress in Yokohama, Japan. And the deadline for submitting papers there is the end of October, so that there is about 4 months left to contribute this World Congress. And then exceptionally, this CPES is a triennial symposium, but because of this COVID pandemic and postponing this CPES symposium, we have the next already after 2 years. The hosting organization is not yet selected, so we don't know where it is, but we know that it's after 2 years in summer, so that hopefully we can see as many of you as possible also in this next CPES symposium. So once again, thank you very much for everyone contributing this very successful happening, and have a nice summer and have a good rest after this big effort. So bye everybody. Or as Mike said, we still have those sessions running on, so visit them and keep on the discussion with them. But let's say this online program will be finished now. So bye to everybody.
Thank you, everybody. Thank you.
Thank you.